Good morning, everybody. How are you guys doing? I hope everyone enjoyed their weekend. Hope you got some time to relax. I am very happy to hear that somebody has heard of Deltron 3030 or Del the Funky Homo Sapien. That is wonderful news. If you have not heard of Deltron 3030, then that means you did not go to college in the year 2002, which could mean any number of other things, but oh man, yes, yes. Um, Great. Daniel, thank you very much for sharing that. Well, I have a something to share with you guys this past weekend. I started working on for one of my kids. Okay, I got a question in a private message about the worksheet. Yeah, I think what I'm gonna do is I will later today or tomorrow post a video. Why am I so blurry? I'll post a video either today or tomorrow with basically how to do that worksheet, just for extra practice. In the event that you got through it, fantastic. You can ignore that video. But if not, then this will be a great resource for you. In addition to that, I've got my office hours at 12:30. I know that doesn't work for everyone, but I'll see what time I've got at the end of class if I can go over some practice problems from that. Okay, so I wanted to share with you, one of my kids, my 6-year-old son, Walter, I got him this or my wife and I got him this robot for Christmas. Um, and I learned as a parent in this moment that putting together this robot is not exactly what he wanted to do. Instead, that turned out to be something that Daddy got to do. And as it turns out, all of the pieces are kind of like this. They're plastic, and there's 276 of them. And I was making really great progress on it until this piece right here. Notice how I said this piece. It should be one. It broke. I tried to super glue it, and unfortunately, one of the things that I forgot is that super glue can be a solvent and it can dissolve things like plastic. And so it didn't actually make it any better. There's the chemistry connection. Um, so yes, it's like Lego building, but less fun. Um, at any rate, I've got your activities for this week up. I've got your quizzes up for this week. There are two things that I not forgot to do, but could not complete. One of them was your practice exam. I'm going to have your practice exam up, I think, before the end of tomorrow. And that's good because our first actual exam is going to be on the 12th. Yes, so a week from Wednesday. So if I get your exam, or if I get your practice exam up on Tuesday, that gives you a full week to work on it. In addition to that, this week will be the end of new content. So this will be the end of our new material. So that means a week from today, on Monday the 10th, we will be going over kind of it will be a nice review session. So we'll go over any of the worksheets, any of the poll questions, which I'm trying to figure out how to extract and export all those poll questions from our class so that I can provide you with those. Um, so next Monday is definitely an important and good time to come to class, so that you can get questions answered and so that I can, kind of give you a rundown. In addition to that, the practice exam that I will post before the end of tomorrow. Um, okay. So I will sorry, let me um the yeah, a week from today will be a review. So we'll go through basically everything for your exam on the 10th. And um, just one second, I have to respond to a private message. The practice exam is absolutely optional. You guys have you'll have 999 attempts at it. It doesn't, if you take it and get every single question wrong, fine. It's not going to be a part of your grade calculation. And so if you want to do it, great. If you don't want to do it, don't worry about it. It's just intended to be like, hey, here's some example questions, or these are our questions covering the material that we covered. And if you can answer all of these kind of without thinking, you're going to be in great shape. If you struggle on some of them, maybe take another look at those or be ready to talk about those. Um, so with that, we are going to go ahead and get started. I'm going to share my screen. And close that, share screen, donezo. Okay, so we've got a couple of questions. We got a couple of demonstrations and models that we're going to look at. The first thing I want to do is I want to go ahead and ask a poll question. Our poll question that I want to ask is this one right here. Which of the following is not one of our subatomic particles? We got a proton, a neutron, an electron, and a patron. Pretty strong showing in the direction of patron as being not one of our subatomic particles. In the event that you voted Patreon, you're absolutely correct. Because a Patreon is not a subatomic particle. Instead, a Patreon is a web page where you sell, I don't know, how-to videos on how to draw a picture of a duck or guitar lessons. It's a nice little creators platform. Um, I do not have a Patreon, but if I did, I think I'd be a billionaire from it. I don't know. Maybe that's reckless confidence. At any rate, there is the end of our. I'm going to go ahead and share the results. 91% voted in favor of Patreon, and you are correct. Now, um, if the poll question, if you're on your app, I believe that if you tap the screen, that it will bring up your menu and you'll be able to see maybe or bring up the screen that gives different options. Or if you tap the screen, I think that toggles to the polls. We'll do a couple more, so I'll give a little bit more time for our next questions. I got a private message. I'm looking at activities 5 and 6. Is there no attached file to the download and work from? I will take a look at that. I know that. So in the column that says activities, there should be activity 5 that's linkable, and then the submission form that also has a link. If you click activity 5, that should give you the file. If you're looking at the submission, I think you're absolutely right, and I need to add the link there. So I will do that. Um, if anyone doesn't mind confirming or disconfirming. Okay, so atomic structure, that's what we're going to be talking about, and that's why we're getting into questions about, well, our subatomic particles. Now, another question that I want to present to you that you probably have a little bit of familiarity with. Um, I always like to, provide you with some questions with maybe you've heard these terms before. And so here's our next poll question. And while you guys are answering that, I'm going to take a moment to look at our Canvas page and add the link as I need to. What is the charge of a proton? So we've got an overwhelming response. We've got 79 respondents so far, and those we got 83 responses. I'm gonna give about 15 more seconds just to make sure everyone can get that. And I'm gonna go ahead and stop the poll right now. And as it kind of expected and hoped, we've got a alarming number of people who know the right answer. And that is that a proton has a positive charge. So I want to give you a little bit of a historical background on an atom and our subatomic particles. At one point in time, we had a subatomic particle or a theory about what an atom looked like. And, everyone had this fantastic idea of, well, why can't you trust an atom? Because they make up everything. I mean, that joke just it has been deadly. That joke has killed for generations and generations and generations. But, the question was, well, what does an atom actually look like? And, for a while there was this theory that it was kind of this spherical thing, existed in the, three dimensions, and the bulk of it was positively charged. And then that kind of evolved into what is now our more contemporary theory, or our more current idea of an atom, and that would be this right here, where we've got a nucleus in the center, and that nucleus is made up of your neutrons and protons. Now, at one point, and I'm going to go ahead and attribute this to the Brits, they had this theory that, well, what an atom looks like is it kind of looks like plum pudding. And everyone in the world was like, well, of course, we know exactly what plum pudding looks like, and we know exactly what it is. I have never had plum pudding, I don't think. It just doesn't sound appetizing to me. And I'm sure that it's delightful. But there was this theory that was you've got all this red space. This is our model of an atom. And all the red space is positive charge. So whatever charge that this species has, that the atom has, it's positive kind of throughout. It's positive kind of everywhere. And then, interspersed in random spots were the electrons. And so there was this guy, his name was Ernest Rutherford, and he said, you know what? I think that that's really not what it looks like. Um, and everyone was like, Ernest, you gotta get on the same page as us, because this is exactly what it looks like. We know it, you know it, everybody knows that this is exactly what an atom looks like. And he was like, I don't think so. And so he was like, you know what? I'm going to develop an experiment, and we're going to prove or disprove the plum pudding model. And everyone was like, okay, okay, fine. So what he did was he got alpha particles. Alpha particles are positively charged particles, and they're depicted as these kind of a combination of gray and red spheres right there. You see on the right-hand side. And he said, you know what? If you're right and an atom looks like plum pudding, then what's going to happen is these alpha particles are going to go straight through this pudding. And you know what I'm going to use? I'm going to use a nice detector system. And this detector is going to detect all of these alpha particles. So I'm going to shoot alpha particles through a sheet of gold. So I'm going to get this nice sheet of gold. And if every one of those gold atoms looks like a dollop, I guess that would be your unit of plum pudding. If it looks like a dollop or a serving of plum pudding, then I will detect alpha particles, because, pretty evenly, because these alpha particles are going to go straight through and they're going to hit the other side. And everyone was like, okay. And so he had this nice little model, and this is our animation of what we would get if, we had alpha particles shooting through atoms that looked like plum pudding. And so he was like, this is what the result is going to be. Alpha particles are going to be detected. They're not going to bounce off anything. They just go straight through. And everyone was like, okay, cool, great, great. Then he said, but hear me now. If I am right and atoms do not look like plum pudding, then I think it's going to look something different. Those alpha particles that I'm shooting through, well, they're going to get detected differently. So here we go. I'm going to use my same detection scheme right over here where I'm just drawing this red line. And let's say this right here, this right here, this right here, these are all gold atoms that make up this gold sheet. If I shoot these alpha particles through and my detection screen right up here where I've just drawn the letter D doesn't show alpha particle, boom, 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 boom. If it doesn't show that, then I'm right. And everyone was like, okay, cool, go for it, Ernest. So he did. He got his source of alpha particles, shot them, and you know what? Look at this. See all these little purple balls? They are the alpha particles, and notice how they're not going in a straight line. That's the big thing. That's the big discovery right there, that these alpha particles didn't go in a straight line. So if he shot 50 from the source, 50 alpha particles, on his detector screen, he'd get like, let's say 20. Fewer were detected than were fired. And so this was a big discovery. And ultimately, what this did was it disproved the plum pudding model. So the plum pudding model, the important takeaway of this. So I want you to know this. I'm going to erase my drawings there. Ernest Rutherford, I'm going to say disproved the plum pudding model. And instead, his work kind of, I'm going to draw this line over here. He proved a nuclear model. Now, other people over the years went through and did more things, and did more research and did more studies. But ultimately, that's what I want you to know about Ernest Rutherford. He disproved the plum pudding model and kind of gave validation or proof or momentum towards understanding the nuclear model of an atom. So, poll question for you. In the plum pudding model of an atom, where are electrons? Randomly scattered in specific locations? Because the plum pudding model was really focused on, your positive charges being randomly dispersed. But if you also, if you look at that model of plum pudding, those electrons are kind of peppered everywhere too. So there wasn't really a kind of structure or design, maybe not design, but an organization for your model of an atom. Now I'm going to go ahead and give about 10 more seconds, but I'm also going to go to the next slide. So Rutherford's work and lots of other people's work looked at protons, neutrons, and electrons. I can go ahead and stop the poll now. And the answer that the majority of folks got was randomly scattered. And for this one, I think that it's kind of a tricky question because if we look at the plum pudding model, and the plum pudding model, where are the electrons? Yeah, the plum pudding model says that those electrons and protons are randomly scattered. And I'm going to share the results. So the plum pudding model says randomly scattered electrons. And the question that I was asking, that would be correct. Okay, so it's important to keep these different models kind of straight in your head. Um, Now I'm going to go ahead and stop my share of that and go back to my PowerPoint. So Over the years, people, in addition to Ernest Rutherford, came up with these different theories of our subatomic particles. And ultimately, what I want you guys to know is this information right here. What are our subatomic particles? They're protons, neutrons, and electrons. I want you to also know where they are. Ernest Rutherford's work really gave a lot of support to the idea that protons are in the nucleus, or that there is something called a nucleus, and that's where your protons and neutrons are going to be found. Now, the mass of those two, they're approximately 1 AMU. Could anyone add to the chat what AMU stands for? I'll give you a little bit of a hint. It does not stand for Agricultural Mechanical University in this case. What do we think? Atomic mass unit. Perfect. No, you do know. It's atomic mass unit. Great response. Great job. That was awesome. So atomic mass unit, you're absolutely right. Now that is kind of what we typically do whenever we're talking about different elements and atoms and molecules, is we almost say 1 AMU is equal to 1 gram per mole. And for our purposes, that's what we're going to say. We're going to say that 1 atomic mass unit is equal to 1 gram per mole. Now, if you look at your protons and neutrons, well, those are 1. An electron, it's effectively got a mass of 0. Do any of the, like, does an electron have an actual mass? It does, but it's something like 0.00000001 AMU. So it's such a small amount of mass that it's, you could just say that this is, I'm going to add the word here, negligible. So you can kind of ignore the mass of an electron. Now, where are electrons found? They're found outside of the nucleus. And if anyone's ever seen the show The Big Bang Theory, which my mom and her husband they used to like to watch that one. Sometimes when they change scenes, they show a model of models like this, basically a model of an atom. And if you've ever seen that, that's what that is. These non-circular lines, these oval-shaped lines are basically, I always kind of think about them as like the the highway or the road that electrons are on. These are the paths roughly that electrons kind of follow. Now, charges of each one of these species, protons are positive. You guys already answered that. Neutrons have no charge, and electrons are negatively charged. Important notes and important things to remember from the periodic table. If we looked at the periodic table, we saw an atomic number. That is the same as the number of protons. If we look at the periodic table, we'll see basically two numbers. I'm going to go ahead and erase that line. Let's say that we've got Li. We got 6.998 and 3. I always like to use Li or lithium because it's a fantastic Nirvana song and it's simple. It's a smaller number. So this 3 right here is our atomic number. Any and every atom of lithium has 3 protons. This other number, that's 6.998. That's our mass number. This is also known as our weighted average. And the way that you calculate that is by adding the number of protons and neutrons. So essentially what this means, for our purposes, we could round that to 7. If I said you have 1 atom of lithium, how many neutrons does it have? Well, you could use this formula. Number of neutrons is equal to mass number, which is 7, minus our number of protons, 3. So we got 4 neutrons. Now, next after that is, how do you deduce the number of electrons? Well, the number of electrons is going to be equal to the number of protons. So if I asked how many electrons does a lithium atom have, you'd say 3, because the number of positive charges and negative charges are equal to one another. Now, Is everyone good with that? Can I get a thumbs up or a yes in the chat for proceed? We got a Y. Awesome. Awesome. Great. Okay, cool. So at this point in time, we know kind of what an atom looks like. We've got protons and neutrons in the center. We've got electrons outside of it. The protons and neutrons, well, they basically give the atom its mass, and then the protons and neutrons kind of counteract what protons and electrons, I'm sorry, protons and electrons counteract one another to give us the overall charge. Now, here is a little bit of a detour almost, or it's something that can be kind of confusing. This is an idea or a concept known as an isotope or known as isotopes. And I know that we've talked about or I mentioned isotopes previously. Um, what we have here is three models of hydrogen atoms. The hydrogen atoms that we have are right here. They are commonly known as hydrogen 1, hydrogen 2, and hydrogen 3. These have different names. For example, hydrogen 1 is pretty much your basic form of hydrogen. Hydrogen 2 is an isotope, and it is known as deuterium. And then hydrogen 3 is a isotope known as tritium. Do I want you to know those specific names? Nope, I don't. Do I want you to know the difference between these three isotopes? I do. Tell me in the chat what is common of all of these three different um, atoms with respect to their nucleus. So look at their nucleus, look at what makes up their nucleus, and tell me what's the same for all of them. Perfect. They all have one proton. They all have the exact same number of protons. Do you think that's important? Yeah. I think that folks, if they're probably nodding their head, yes. That is important because, and if you have a periodic table before you, take a moment and say, well, would I be talking about hydrogen if I had an atom with two protons? Remember, your number of protons is the atomic number. No. If you have a periodic table before you, if I was talking about an atom with two protons, what atom would I be talking about? Or what element would I be talking about? Helium. Absolutely right. Great, 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 great. So the number of protons tells you what element you're talking about. All of these have one proton. I'm going to draw a nice dividing line between all of these. These are all hydrogen atoms. Now, this is what makes them different from one another is the number of neutrons. When you add up the number of protons and neutrons, you get the mass of that specific atom or that specific isotope. So these three things are isotopes. I remember whenever I talked about this, I mentioned Oreo cookies. And I mentioned if you had a regular Oreo, a double stuffed Oreo, a blonde regular Oreo, and a blonde double stuffed Oreo. Those are all Oreos. So they're all effectively the same thing. Think about those as isotopes that differ from one another. Or, I'm sure that there's some other permutation that you could think about that and some other comparison. But isotopes have the same number of protons, but different numbers of neutrons. Can I get a Y or a thumbs up in the chat if we're good with that? Okay, great. Now I'm going to switch over. Actually, I'll throw a poll question at you real quick while I'm changing screens. So there's a poll question up. I'll give about 30, 40 seconds on that. Got about 10 seconds left. All right, I can go ahead and stop it right now. Got good responses on that. And 55% of the class said protons and neutrons, and you're absolutely right. So those are the particles, the subatomic particles that make up the mass of an atom. Those are also the subatomic particles that are in the nucleus. Now, one thing that you probably noticed in our last slide was your hydrogen 1 isotope doesn't have any neutrons. And that's nothing special necessarily, but that's just sort of a thing to, the mass of an atom of hydrogen is really just distributed to the proton. Okay, now I'm going to stop sharing and I'm going to share this link in the chat because this is kind of a fun tool to play around with. Um, that is a great resource with lots of different stuff on lots of different simulations, and not just for chemistry. But I always like this because this is kind of the way that my brain works. We've got our three subatomic particles, protons, neutrons, and electrons. And the first thing that we can do is we can throw in a proton. And we've added a proton, and this tells us a couple of things. It introduces a new term that we haven't talked about quite yet, but we're going to, and that is ion. It is a positive ion. Could anyone add to the chat if they have ever heard of and know what an ion is? And if you know what an ion is, could you go ahead and add kind of a quick definition to that? But with this, what we can do is add more and more protons. So I've got 3 protons in my nucleus there, and well, okay, great, awesome. Thank you very much. So an ion, which we're going to um there's a couple of different terms related to an ion. Ah, yes, 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 yes. Thank you very much, Delshay. That's a great response. An atom with a negative charge. You're like 98% of the way there. And the only thing that I would change about your statement is I would remove the word negative. Because watch this. So I've got my lithium nucleus basically. Now I'm going to add an electron, add another electron. And watch as I add this third electron here. Boom, it's neutral. Now watch as I remove it. That plus there is indicating that my ion has a positive charge. It is a positive ion. So if I add an electron, now it's a neutral atom. And I know it's neutral because, well, protons are positively charged. I have 3 protons and I've got 3 electrons. With their powers combined, they cancel one another out. Now, if I add one more electron, add to the chat, what do you think is going to happen whenever I add one more electron? It's going to be a negatively charged. Now, my follow-up to that is, will it be lithium still when I add one more electron? Yes, it will still be lithium. Boom, negative ion. Okay, fantastic. Now, what do you think is going to happen? Because could anyone add to the chat, looking at this ion, we've got a negatively charged lithium ion. Tell me what the mass is based on the subatomic particles that I've added. Dang, man. Yeah, it's three. It's 2 point. Yeah, you guys are right. It's three. It's three atomic mass units because what I have in there is I've got three protons. Each of my protons have a mass of approximately one atomic mass unit. My electrons, the mass of those, I've got four of them, but it's kind of like it doesn't really matter. Those are kind of negligible. Now, so you could make the case that this is an isotope of lithium. Let's call this lithium 3. What do you think, or what's the mass going to change to whenever I add a neutron? Yep, my mass is, yeah. And here's this display with my mass number. So now 5, 6, 7, 8. Does the identity of my atom ever change in terms of what it is? No, it remains lithium the whole time. As I remove neutrons, when I remove a neutron or add a neutron, I am making a different what? I'm making a different mass, yeah. But what's the term? Isotope. That's sorry. That was kind of a poorly leading question on my behalf. But yes, I'm making a different isotope when I change the number of electrons. Well, look at the net charge. And this is one thing I want you guys to keep in mind is if I add more electrons, the magnitude of my charge increases. I've added, and I like the way that this displays our positive and negative charges because it shows them canceling out, and then it shows 1, 2, 3, 4, 5, 6, 7. Seven negative charges beyond the three that are canceled. Okay, if I add a proton, am I making a different element or isotope? If I add one more proton, I'm making a different element. So throw that in. Now I got beryllium. I've got boron, carbon, nitrogen. Okay. So I've added that to the chat. I think that this is a good thing to play around with, in part because um, I think that you guys can see my screen well enough to see that I don't know if it went a little gray there for you, but I this is an easy thing for me to grab a screenshot of and be like, okay, I'm going to white out this area. What is this element? How does the negative and positive charge affect the element? Great question. So the negative and positive charge doesn't change the identity of the element at all, but instead what it changes is that element's ability to make a bond. So if something is negatively charged, well, then what it's going to do is it's going to seek out something that's positively charged. So those are like two different ions. And I'm going to add this to the chat, or I'm going to add this term for you guys. Um, Actually, I'm going to jump back into this. Okay, so I see I got a private message. So um, a positively charged atom forms, or actually, I'll drop the word forms. Ionically, ionically bonds with a negatively charged atom. So a positively charged atom and a negatively charged atom, they're attracted to one another. And you have an example of this in the form of NaCl, table salt. Well, table salt is two different ions, Na plus and Cl minus. So, yes, absolutely. Um, Now, there are two other terms that I want to introduce, and then I got a private message question that I got to answer. A positively charged atom, I'm going to put this in parentheses, is known as a cat ion. And a negatively charged atom is known as an anion. Okay, so a private message question that I got was, so adding protons changes the element. Yes. Adding neutrons changes the mass and makes it an isotope. Yes. And then adding electrons makes it a negatively charged atom. Absolutely. That is like, this was sent to me as a private message, but I'm going to copy this. I'm going to paste it to everyone because these are like y'all's own words. I'm going to add one more thing, and that is, and removing electrons makes a positively charged ion. Okay, that is, so then, yeah, yes, yes, you're absolutely right. Can you force two positively charged? Ooh, Daniel, that's a great question. Can you force two positively charged ions together? Um, I think that it's going to have, I think you would have to have something to kind of counteract that. So, um, positively charged things will always kind of gravitate towards those negatively charged things because it's almost, think about it like a negatively charged thing has lots of electrons and it has those electrons that it can share. And so positively charged things are like, ooh, I like sharing, and you have something that I want to share with you. So fantastic. Um, and so it's almost like, so I feel kind of comfortable saying, can you force two positively charged things together? I I would say no. Um, but it gets kind of complicated because those two positively, like, if you just have two positively charged things and you're like, go, interact, have fun, um, they're not going to like that. But if they are equally sharing with a negatively charged thing, then that's a little bit of a different calculation. And to that, I would say yes. So that link that we were just on, man, I love these questions you guys are having because they're fantastic. That link that we were just on also takes us to a page where we can play around with this, where we can look at our mass number, look at our charge, and look at our atomic number. Now, notice one thing about this is that when we're talking about an isotope versus the periodic table, if you look at a symbol on the periodic table, for instance, this right here is an atomic symbol. And this is very similar to what you see on the periodic table. I'm going to draw something a little bit more of what you'd see on the periodic table. You'd see something like this, 3Li and 6.998. Now, the big difference there, well, it's going to be, one thing is the charge isn't indicated. The second thing is this number right here. If you ever see a symbol like this right here, where I've just drawn a star and now I'm drawing a red box around it. If you ever see a symbol like that, think about it as, okay, I'm looking at the information for one specific isotope. Now, if you see something like what you've got in the upper right-hand corner there, anytime you see that number with a decimal place, then we're looking at our mass average. So that's taking into account all of the different isotopes that exist. Now, with that in mind, this is also taking into consideration, this becomes a challenging calculation, and that is using the term isotopic abundance or relative isotopic abundance. And so this basically says, well, let's say that you think about all the different isotopes of an atom and you say, okay, well, there's 33% of them, or actually, let's go with hydrogen 1. I'm just going to label it H1, H2, and H3. If hydrogen 1 has a mass of 1, hydrogen 2 has a mass of 2, and hydrogen 3 has a mass of 3, and 99.99% of all of these isotopes in the known universe has a mass of 1, the mass is going to be pretty close to 1.000, which is what we see on the periodic table. So the reason that you see that decimal place or that decimal number is because we're taking into consideration all of the different isotopes and their approximate masses and the abundance of them. So I don't want you to, or I want you to recognize like that's why that number has a decimal. Okay. And that's one of the reasons that we also treat it as, well, we can round up. So we can look at something like boron, and this might be tough for you guys to see. Boron has an atomic number of 5 and a mass average of 10.81. Well, that's because boron has a couple of different isotopes. One boron has has a mass of 11. Another one has a mass of, does anyone want to guess based on the mass average being 11? Could anyone add to the chat and make a guess of a mass of a different isotope of boron? Our average is 10.81. I said that there's isotope boron 11. What do you think is another isotope's mass? I like it. 10. Perfect. Okay, so yeah, let's go with 10. Now, if let's say hypothetically 50% of all boron isotopes had a mass of 11 and 50% had a mass of 10. What do you think the weighted mass average would be? If it was a 50-50 split, there were only those two. Exactly. It'd be 10.5. Based on it being 10.81, which isotope do you think is in greater abundance? The 11 or the 10? The 11. Perfect. That's the sort of question that I will ask you, where I'll show, I'll say, here's two different isotopes. What do you think there are more of? The 12, like the 11 or the 10? So to kind of anticipate that question, let me go ahead and clear this out and we'll do a practice problem. So, the question will have a stem of like, go ahead and annotate. I'll type this in. Got to turn that. Oh, dang it. Oh, dang it. Computer. Oh, you're seeing present. Oh, that's not what I want. So, okay. Sorry about that. Thank you. Thank you very much for letting me know. Okay, so I'm going to turn the pen off. This is probably a little bit easier for you guys to see. Okay, so now I'm going to annotate. I'm going to go to chat or type. Okay, so nitrogen has two known isotopes, N14 and N15. Which isotope is more abundant? And then we get tab, tab, tab. We got A, N14, B, N15, C, they're equal, And B, nobody knows. So that to me, Joel, that is the sort of question that I want you to be able to answer. And so could you add to the chat what you think the answer is? Is it N14 or N15 based on the weighted average mass? Okay. Okay. We got lots of responses of N14. Okay. Now, in the event that this question's kind of confusing to you, think about when you average two numbers or when you average numbers. You add them up and you divide by two. Okay. That's effectively like saying, it's a 50-50 split of those two numbers. Like if you and I'll just put this in terms of I just want to make sure that you guys feel comfortable with this question. Um, okay, I better clear that. Clear all drawings. Let's see. Actually, um, okay. So that's the sort of question that I want you to be able to answer. So the isotope mass closest to the OG element's mass is more abundant. Yes. Yes. I got a private message that said, so the isotope mass is closest to the OG element's mass is more abundant. Yes, that's absolutely right. Now, isotopes, there can be some elements that have as many as like seven different isotopes. Um, but the questions that you should expect on exams would be something like there's two isotopes. There's maybe three isotopes. Which one do you think's the most abundant? Um, and you know, whenever I'm looking at the periodic table right now, there's one element that stands out to me, and that's chlorine. Chlorine has an average mass of, or average isotope mass of 35.45. If I told you it has two isotopes, 35 and 36, that's an example where those two isotopes are almost equally common to one another. But the 35 is a little bit more common because that average mass is closer to 35 than 36. Cool? Okay, thank you. Thank you. Great, 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 great. Okay, so now this next part, what we're going to go into is going to probably move a little bit faster. And that is electrons. So for the first part, we kind of focused on, you know, protons and neutrons because they make up the mass of an atom. They make up mostly what we're interested when we're thinking about an atom. Electrons are a part of it, though. Electrons are negatively charged, and they determine many of the properties of an atom because of the fact that electrons can be shared between two atoms. So there's on the left-hand side here, you see this image of what's known as a hydrogen discharge tube. And this is basically a tube that has nothing in it except for hydrogen gas. So I'm going to put this as H2. And then what somebody does with this is they send an electric current through it. So they kind of electrocute this hydrogen gas. And does anyone know what a prism is? I'll give you a little bit of a hint. Pink Floyd's Dark Side of the Moon. And I can actually, yeah, absolutely, it refracts light. Um, Go ahead and grab that and copy, paste into my. Okay, we'll shrink that down a little bit. And here we go. So Can everyone see the Dark Side of the Moon album cover there? If you're not familiar, that's Pink Floyd's Dark Side of the Moon album cover. And what this shows is a prism and white light. It's good. It's good. If you haven't listened to it, it's good. Um, so what this shows is a single beam of white light hitting a prism, and then on the other side of it, a rainbow. And what that rainbow is displaying is basically here are all of the lights, or here is all of the colors, here is all the wavelengths of light that are kind of encapsulated in this white light. Now, essentially, what someone does with this is they get this hydrogen gas and they put a prism over this. And rather than it displaying this entire rainbow, instead we get a blue light, a light blue light, and a red light that comes out of this. Now, a fair question there is, huh? Well, the reason for that is that light of different colors or lights of different colors have different energies because they're all different wavelengths. And so this is saying, well, when you basically electrocute hydrogen gas, you have different energies released from it. And so those three different colors tell you something, or tell you that those are different energies that are coming from this. And if you do different gases, helium, nitrogen, hydrogen, neon, I know we already did hydrogen, but if you do different gases, you're going to get something different as well. Similarly, if you burn different sources, or if you have different materials and you burn them, boron, sodium, lithium, iron, barium, calcium, copper, they're going to produce different colors. And a fair question there is why? Well, I'm going to jump ahead. Because, jumping all the way down here, when you have a hydrogen atom, we've got an electron. I'm going to go ahead and replace that hydrogen with that dot in the middle. That's my nucleus. So if I electrocute this, what's going to happen is this electron is going to shoot way up to what's known as a higher energy level. And when that higher energy level electron relaxes, so think about it as it starts out right here, and then it gets shot way up here, and then it relaxes. And then another electron. And keep in mind, there's lots of different atoms of hydrogen. We're shooting all these different hydrogen atoms, their electrons up to different levels. And then whenever they get to a level, they'll relax and they'll release energy. And that will give us these different colors. So this is known as electron excitation. When you excite an electron, it goes to a higher energy level, and then it relaxes, and comes back down, and releases energy. And that energy is visible to us. So here's one, here's another, and then last but not least, here's our last one. Now the color coding of these lines, don't lose any sleep over that. But essentially what that tells people, or what the significance of that was, hey, these electrons, they exist outside of the nucleus. And whenever you kind of jolt them, they jump up to a higher energy level. And then they release some energy. So what I want you to take away from this is, one, I don't want you to commit to memory these wavelengths that are indicated here. Don't lose any sleep about that. Instead, what I want you to think about is electrons jump up, they change energy levels, and then they go back down. So they get excited, and then they come down. They get excited, And when they're coming back down, they're releasing energy. Okay, so we have, I'm going to give you this poll question right here. Yeah, there we go. That poll question, which might be in this one. And I'm sharing the right thing, I think. Yeah, I hope so. Good. And this is like if ever you're burning something and you see the colors change, it might be because of heat, but chances are it's because of what is in that material that's burning. Um, if you were to get like let's see, what's the I'm trying to think of an easy way that you could burn something and see a different color up here. I can't well, absolutely like fireworks because they're going to, different compounds that are in there are going to give different colors. Um, and then one thing that I know, I think it's like burning paper from different time frame or like different times. If you burnt paper that was 200 years old, that might release a different color because there were different materials used in the actual production of it. Okay, I'm gonna go ahead and stop this poll. And then, this is like this ultimately gives rise to this idea of what are known as orbitals. So electrons exist in orbitals surrounding the nucleus. So this is just a good model of kind of what an atom looks like. So this is kind of the next evolution. This is Niels Bohr's uh, proposal of what an atom looks like. We have orbitals that are kind of like these different orbitals are different energy levels. And when an electron goes all the way up here, well, when it gets shot out there, it's eventually going to come back down. And whenever it does come back down, it's going to release light of a particular wavelength, of a specific wavelength. And that's what we see. And that's really helpful for looking at and identifying different atoms and different elements because hydrogen, for example, here has light that goes to only some energy levels, whereas other substances, something that's not hydrogen, well, it can shoot electrons out to an even higher energy level, which is why we get something that's, maybe here or here or here. So these are the three colors that are produced because of the different energy levels that hydrogen's electrons go to. Now, um, the next point of that is, well, this gives us a way to look back at this structure, this kind of orbital structure of an atom. And in these first few levels, there's only a certain number of electrons that we can place there. And the answer to that is the first two spaces, you can put two here. And then you can put two here. And if you remember, whenever we were building an atom, well, only a certain number of electrons can go in each level. And so Niels Bohr had this idea of this is what an atom looks like. And then that idea continued to evolve. And that ultimately gave us what is known as a quantum model of electrons and quantum model of an atom. That is where I'm going to stop. We are going to get back into this on Wednesday. Before the end of the day tomorrow, I'll have your practice exam up. I got to catch up on some grading with your discussion opportunities. Other than that, though, thank you guys so much for coming to class. I really appreciate the responses. You guys are doing a great job. If you have any questions for me, excuse me, you're welcome to hang around. I'm going to stop my recording right now.